So in the previous video, we learned how to interpret interaction term between two binary variables. But now we are going to extend the model so that one of the variables is continuous. So let's think about this Bayesian model. Base model is y equals to beta 0 plus beta 1 d, which is binary, 1 or 0, plus beta 2 x. X is not binary anymore. It is a continuous variable. It can take any number. And then we are interested in the effect of x on y. Say x is the student to teacher ratio, and what is the effect of increase in x on y? And as before, we are it may be possible that the effect of x on y can depend on d. D is say the percentage of English learners, whether it is high or not, above 10 or not. In this case, from the base model, the effect is beta 2, fixed at beta 2. It is constant no matter what x is and no matter what d is. But we are particularly interested in the dependence on d, so we include d like this, the interaction between d and x by multiplying them and including another coefficient, beta 3. So in this case, we may think about two cases for d, but x may take a lot of values. It's student-to-teacher ratio. It can be like 15, 16, 17, or any number. So we are going to consider only two different cases for d, whether d is 0 or 1. So if d is 0, the regression equation simplifies. So if say d0 means the percentage of English learners is lower than 10%. If that's the case, then the regression outcome is determined simply by this rule. And now, and if d equals to 1, where the percentage of English learners is greater than 10%, then you put 1 here. So the regression becomes more complicated. Still, you may just put them together. So consider these two parameters as one intercept. So the intercept is now beta 0 plus beta 1, and the coefficient, the slope of x is now beta 2 plus beta 3. So then it is clear, what you can see is that beta 1 captures the difference in the intercept across d equals to 0 and d equals to 1. And beta 3 is the difference in the slope between d equals to 0 and d equals to 1. So beta 1 and beta 3 capture difference between two different groups at different points. So let's think about that more carefully. Graphically, you can think about this. So now first, in the first case, suppose that there is no beta 3. That means two different groups, there is no difference in the slope. So beta 3 was the difference in the slope, but it is there. If it is 0, then slope does not change. It's parallel, but the intercept does. Intercept changes by beta 2. So say low percentage of English learners and high percentage of English learners, or vice. So the slope is the same. Now, on the other hand, now consider beta 2 is 0. There is no beta 2, but there is, so beta 2 is, so the intercept is the same, but the slope may be different. So different groups have different slope, but the same intercept. Then you have this graph. So which means when the student to teacher ratio is 0, the expected test score is no different between low percentage of English learners and a high percentage of English learners. However, when the student to teacher ratio increases, there is they diverges from each other, and combination of these two is given by this. So the intercept is different and the slope is different. So both are different. It's most general, most flexible model using the largest number of coefficients. So interpretation is simple, and in the end, so in general, so x appears here and not again here. So now think about the derivative. So if you differentiate this function with respect to x here, then it is clear that it's easy to get this result. So the differentiation is pretty simple. As a result, the effect of x on y can be written as beta 2 plus beta 3 times d. So when d equals to 1, this part is on, but when d equals to 0, this part disappears. So the effect of x depends on d. That's the point. And beta 3 is now interpreted as the increment to the effect of x for d equals to 1. So the difference in the slope. So the effect of additional teacher it may be different across different groups. That is captured by beta 3. So back to our example. The high EL means as usual. So it takes 1 if the percentage of English learners is greater than 10%, and it is 0 if lower than 10%, and we include multiplication of them, and somehow the standard errors are not aligned well. First, student to teacher, the coefficient of student to teacher ratio is minus 0.97, which means for the group whose English learners is less than 10%, then the effect of student to teacher ratio is minus 0.97%. So if the student to teacher ratio increases by 1, then test score decreases by less than 1 point. But if the percentage of English learners is greater than 10%, then this term kicks in. So this part kicks in. So the effect on the test score becomes this plus this. So the total effect is 2.25 points. So as you can see, again, the effect of student to teacher ratio is greater if there are more English learners. So it is also consistent with our expectation and estimated to be true, even though the significance of this beta 3 is weak. It's insignificant. Statistically insignificant. The standard error is too large compared to the estimate. So, however, like if you ignore the significance for a while, then you may conclude that the student to teacher ratio effect depends on the percentage of English learners. And also, so this is exactly what I said. The coefficient is insignificant, and also this coefficient is insignificant because estimate is 5.6, but standard error is 19, even greater than the estimate. So both are insignificant. But what is interesting here is, then can we delete these two terms? Then no. Then, so if you do a hypothesis testing, whether it is 0 and it is 0 at the same time, then the answer is no. The p-value is less than 0.1%. So that means the English learners is an important variable, like either for the intercept or for the slope. However, but it's not clear where that effect is going. So, so that's what we get here. And finally, the last one, the last case is where two variables are both continuous. So now we cannot do case-by-case study here because each of them takes many different values. Still, the idea is the same. We have the base model, just simple, separated by plus. But if you add the interaction between x1 and x2 by including their multiplication, then you can capture the effect of one variable depends on the other, right? This is what we want to accommodate in this interaction term. So the idea is also the same. Differentiate. Say differentiate with respect to x1, then you get this derivative. The effect of x1 on y equals to beta 1 plus beta 3 x2. So this is the effect. And as you can see, it's effect of x1, but it depends on x2. So they have cross effect. And so then you can see, and you can easily see that if beta 3 is positive, that means the effect of x1 increases as x2 increases. But if beta 3 is negative, that means the effect of x1 decreases as x2 increases. So it captures whether they are complementary or substitute. So that shows, and in our example, so the derivative is so the interaction term has a coefficient of 0.0012, which is still insignificant, but let's just ignore the significance. And 0.0012 is the interaction term. So then, and the coefficient in front of student to teacher ratio is minus 1.12, which means when percentage of English learners is 0, the effect of student to teacher ratio is minus 1.12. However, when the percentage of English learner is not 0, for each additional percent in English learners, you have to deduct this much from this coefficient. So think about 20%. Suppose that there are 20% of students who need to learn English. Then the effect of student to teacher ratio is minus, something is wrong. Oh yeah, it's right. So minus 1.10, which is too close to this case. So even if percentage of English learners may have some impact, but the size is pretty small in this case. So we cannot, so this is insignificant, and also this is insignificant. So both are insignificant. However, jointly they are significant, more significant. The joint p-value is 2%. So the percentage of English learners is an important variable. So that's what we see from the result. Okay, so this is it. I will call it a lecture, and I am going to make another homework 5. Yeah, homework 5, and we are going to finish the chapter in the next lecture, and I will do homework 5, and then we will go to the next chapter. And my plan from now on is that so after this one, we have 7 classes, 7 lectures left. So I plan to do 2 more chapters from the textbook. So so far we have done chapter 4, 5, 6, 7, and 8. 8 is this chapter, nonlinear regression functions. And then I'm going to skip chapter 9. Chapter 9 will be skipped, and I will go directly to chapter 10 and chapter 11. So my goal of this semester is to finish chapter 10 and 11, approximately 3 lectures each of the for each chapter. And if time permits, uh, maybe chapter 14, but I'm not so sure. So that like only if time permits. Okay, this is it. Okay, have a nice weekend. See you later. Bye.